Welcome you all to this Cryo-EM and image processing course. Today I am going to take the last class of this particular course, and yeah, definitely it is very difficult task to explain the entire image processing and 3D reconstruction part in this short period of time. So maybe in future I can take another course where we are going to discuss about this image processing and 3D reconstruction part. There are many things that you have to cover, and that entire part there are many theorems are also there what you have to understand if you want to understand that image processing. But today I'll just give you a overall a idea that how we are generating a 3D reconstruction from these 2D images, and mostly I'll use my face as an example, and that will be sometime a easy example to align those things and explain things using the image. But here there is a huge mathematical and physical sciences involved in this entire image processing step. It will be not that straightforward, but definitely if you are just a very users or beginners, that you don't have to understand each and every step. If you just go and click couple of buttons, you may get a 3D structure. But if it is a standard protein or standard sample, probably you don't have to be pay attention to all of this. But if you have a difficult sample, then definitely it is important to learn what is going on inside. So there are many data processing tools are available nowadays, starting from Spiderweb, Eman, and then XMeep, Reliant, Cryospark, and many more are coming nowadays. But those are the major data processing tools. System is also there. Those are the major data processing tool that students and researchers are using, and definitely in all of this, if you just consider that Spiderweb or Eman or Reliant, you can sometime you have to look at the metadata and you have to figure it out where there is a how we can improve the data processing and other step. So most of the time those are very user friendly, and if you are not very expert, you don't have to pay attention to any of these things. And but if someone is very much interested that okay, I want to be a master of this data processing, then it is better to understand the algorithm behind that, how those data processing tools are working. Definitely most of these tools are running in the Linux system. It will be not in Windows support. So you have to learn a little bit Linux also, and I'll always recommend that whenever you will use any data processing tool, it is better to use the command line. Don't use the graphical user interface all the time. So if you use the graphical user interface, you will not learn too much about this data processing tool. As I mentioned that I'll use my own photo to show you those alignment and other things. So here this is basically inspired by Sir's couple of slides from his Cryo-EM lecture, and I followed the same path that how he tried to explain. So here, so most of the time that reference based alignment, previously I told that if you just consider 2D averages, basically it is a reference free alignment. Okay, and here we are talking about the reference based alignment for the 3D reconstruction. If you remember that last cycle, what I told, I have a initial model, and initial model we are taking 2D projection of this initial model. So when you are getting a 2D projection of this initial model, and then a raw particle, we have the raw particles, right? We are trying to align this raw particle with this reference of this initial model. So if we have the reference and then we are trying to align, so again there is some kind of x and y translation and rotation, everything will be implemented here to align your particle. Simultaneously you have to calculate the cross correlation value also. Without that cross correlation value you cannot do this kind of alignment. So here you can see this is a reference, you can see this is the initial model, and initial model means there is a no details features you can see. So if you look at my face here, so I am wearing a glass, or I have a mustache, or my hair, nothing is visible in this particular image because this is a very low resolution initial model you can consider. Now here you can see there is a cross correlation value. So these are the raw images, and these raw particles I am trying to align with my initial model, and here so mostly we are applying the cross correlation method. So whenever we will implement this cross correlation method, we are going to in Fourier space, and then we are doing this alignment thing. So we are not doing anything in real space, it will be in a reciprocal space. So we are performing this alignment and trying to get the accurate angle and x and y translation between these images. So here I am giving you an example. So here again we are doing this cross correlation method. So if you just consider that this is a raw particle, right, and raw particle, if this is the same head I have and it is a frozen head and I am collecting a cryo images. So now you can see there is a different orientation of this head, it is not, it cannot align with this head at all. So here you can see it needs some kind of rotation in this, it needs some kind of rotation, and all the cases that rotation angle will be not same, and also there will be a some x and y shift is also there. So here first thing first, what we have to do, we have to rotate those things. Now you can see we are trying to rotate those individual images, and we are applying a mask to separate the noise and the signal, and we are trying to align them. This is called the alignment part. So we will rotate individual images to try to align and get the better cross correlation value, because if we try to align this particular image with this one, they will not align properly. Here the cross correlation value will be very poor because they cannot align properly. Here also they cannot align properly. This may align properly because their orientation is same, this particular image 1 and 2, but if you just consider this particular image and this particular image, and if we try to align them, they will be completely mismatched. But if we have this rotation, now if we try to calculate the cross correlation between this particular image and this particular image, we will get a very good cross correlation value. That is basically we are trying to do all the time. So we rotate, we mask out all the noise. So what we did here, so first thing we take this image, we mask out all this noise. So we removed all the noise, we only focused on this, that will basically help. So this is the mask out. Now we align all these images, and from there we calculate a first three-dimensional structure. When we aligned all this particle, we first calculated, and definitely this particular image noise is removed, signal will be much better, we will get a much better reference. Now we use this reference and then we try to redo this entire thing, that is basically telling iterate. So we are iterating this same cycle again and again multiple times. When we iterate this one in multiple times, we can separate them or we can align them much better way, which help us to calculate the cross correlation value. Our cross correlation value will be much higher if we calculate or align the particles properly. So that is basically we are trying to do here. So the next round, if we just see, this is our first reference, and then we are taking this 2D projection of this one and try to segregate the particle based on that reference. So this is called, we are implementing definitely that cross correlation method, and we are also applying projection matching. Here we have one projection, and based on that reference we are trying to matching our raw particle. That is called the projection matching theorem. And then when we are doing this projection matching, we are basically applying common line methods. So we cannot have enough time to discuss about the projection matching or common line method technique. You just remember that we are using this projection matching and common line method to calculate the three-dimensional structure. So we are not going towards that mathematical details how to calculate all of this, and here we are also using the maximum likelihood. Previously for 2D classification we are using k-mean clustering or hierarchical clustering, but nowadays most of the cases we are using that maximum likelihood method. So this but here we don't have the enough scope to discuss about the mathematical part of this maximum likelihood methods. Now come back and see that entire 3D reconstruction process. So what is that entire 3D reconstruction process? If you look at, this is called the projection matching, right? So what we have an initial model. When you have that initial model, first initial model we are classifying into, we are taking 2D projection of this initial model. When you are taking that 2D projection, it has a 3D structure, and those 2D projection will be much better. So here you can see these are the 2D projection of this three-dimensional structure. From this three-dimensional structure we are getting this 2D projection. Now we have a raw particle here. This raw particle 1, 2, 3, 4, 5, 6, 7, that raw particle we are trying to align with this 2D projection. When we are trying to align, you can see in this particular projection, 2D projection is matching very well with this raw particle. Again, if we just go down, particle number 6 is also matching with this 2D projection. Similarly, here we have a particle number 2. This particle number 2 is matching very well with this particular projection here, projection number E. So similarly, all these particles one by one go through this 2D projection and trying to align with this reference. When it will align with this particle, it will just segregate in that particular group. That okay, most of this particle here you can see the particle number 1 and particle number 6 is fitting in this class A, and then particle number 2 fits, particle number 2 and particle number 5 fits in class E, then particle number 4 fits in class B. So now you can see we can segregate those particles in different group, and then we can calculate a 2D averages of that one again. When you calculated the 2D averages, we are getting these 2D averages, and we back project because it is covering most of the angle of this three-dimensional structure, and we are getting a high resolution structure. When we have this high resolution structure, we are taking this high resolution structure and generating reprojection of this refined model. When we have this reprojection of this refined model, we are redo this alignment again and we calculate these 2D averages, and from that we are getting a refined structure, and we will iterate this cycle multiple times until we will get a final converged three-dimensional structure where there is no change in the alignment parameter, means rotation angle or x and y translation. This is Helen's one paper, they published that one, most probably it is 2010, and it is a very nice article. So they describe everything very nicely, how to do this projection matching theorem. If anyone is interested, definitely go through that paper. Okay, so this is will come here directly. So here one thing you just remember that okay, when we have a 3D object, so what we are getting basically this 3D object, we are getting a 2D projection of the 3D object. So always you remember that we do the Fourier transform because we are not doing any image reconstruction in real space, everything we are doing it in Fourier space or reciprocal space. So here we have a 3D object, we are getting a 2D image and two different orientation of this duck. This is from the side and this is from the front, and we do the Fourier transform. When we do the Fourier transform, and then we will apply the cross projection matching and cross common line method. So here this is the projection of the 3D Fourier space, where we are trying to align this all this 2D projection in a 3D space, and finally we will get the 3-dimensional structure. So here the similar things is shown here, that you have a 3-dimensional structure from where we are getting the 2D projection at different orientation, means at a different angle. So we are looking this same object from this particular angle, we are getting this particular image. If you are looking at from this particular angle, you will get this kind of image. So then everything is transferred to in Fourier space, and then we are trying to align them in a 3D volume. And when you will align all these things perfectly, then we will convert it to in real space from the Fourier space and get that 3-dimensional structure. So what is that 3D classification? 3D classification is nothing that the 3D classification is a process where particles are sorted into distinct homogeneous population from a heterogeneous mixture of the particle. What is that particle? Particles means after 2D classification we have a very nice 2D averages, but within that, if these proteins are flexible, that you can segregate into different classes, that is called the 3D classification. I will show you couple of example. Why do we need 3D classification when the 2D classification can sort the heterogeneity? So heterogeneity can be reduced at 2D level to sort for obvious differences visible at 2D level. However, the smaller difference, conformational flexibility, cannot be sorted by 2D classification, okay, because this is a reference free and we don't have any reference, so it will be bit difficult to sort out that conformational heterogeneity or structural heterogeneity. So some of the difference cannot be seen at 2D level because of their complex geometry. These differences can be sorted out using the 3D classification. That's why 3D classification is so important technique. Now I'll just skip this part, that okay, how we can perform the 3D classification, because this is mainly the method part where we are using the maximum likelihood and Bayesian method to perform the 3D classification. I'll directly go to the data, which will help us to understand about the 3D classification part. So as I mentioned that there are different tools are available that you can use it for 3D classification. Reliant is also there and Cryosparks are also there. These two are very popular data processing tool nowadays. Many students are using those. So here I am showing you a direct example where we have a 3D classification of one of our protein sample. So here you can see this is the raw micrograph where proteins particles are embedded everywhere. Now here we initially pull out almost 3 lakhs particle and then we classify them. Here it is written 3 rounds of cleaning. So we did a multiple cleaning and then we removed lot of bad particles. So here you can see some 30,000-40,000 particles we removed, and then we calculated in an initial model, and then this particle is aligned with the initial model and tell the system to split the data set based on their conformational changes. So here you can see in this particular case you can see lots of details here, but if you look at the same, it may be a similar kind of architecture, but those details are not visible. Here also those details are not visible. Here something extra is attached. So this is the technique, it is called 3D classification, when based on one reference or initial model we can split the data set into multiple classes, and from these multiple classes whatever particles are coming good, we are taking that one and we are performing the 3D reconstruction, and finally we are getting a high resolution structure of that particular model. So similar approaches is taken here also to calculate the three-dimensional structure. So here the raw particles are there, and then you can see there are total 8 lakhs particles from 1200 images, and we went for 2D classification, and finally 4.8 lakhs particle is used this as a initial model and classify, and finally we use this to get a high resolution structure. Now looking at those images, you have to tell that when you will refine those at different iteration, it will improve the resolution, and that you can see it at very low resolution. When something is 20 angstrom, you will see a blobular structure, and then if you align your particle, it will gradually improve. So this is something, it is showing 12 angstrom resolution. Then later on, where all these details, if you look at those details are not visible here, but here you can see lots of details here. So looking like that, there are some improvement here. So this is basically roughly 9 to 10 angstrom resolution structure. Now if you refine more, this is the structure where all the helix are looking like a tube. This all the helix are looking like a tube. So this is basically roughly a 7 angstrom map. Now here you can see all this structure, there are lot of spiky things are coming out from this one, where this structure you can tell it is a high resolution, maybe roughly 4 angstrom or in between 3.5 to 4 angstrom, because all these side chains are visible. So when resolution will improve, means resolution value will decrease. So 4 angstrom, 3 angstrom, you can see most of the side chain or long side chain like tyrosine, tryptophan, arginine, lysine, histidine, and here at 7 to 8 angstrom you can see only helix like a tube, but it is also a much better resolution than this one. So definitely it is a 7 to 8 angstrom, you can see helix as a tube, and then 10 angstrom your map will look like that, where helix will be not visible, but all the domains boundary will be clearly visible. This will be somewhere 10 to 12 angstrom or 13 angstrom, and this is a very low resolution structure. There are couple of more 3D classification I am showing that. Okay, we have another protein where we have collected 4500 images, and then we calculated all this power spectrum and check it, and we remove the bad images. So here you can see image number is decreased. Then we have total 11 lakhs particle. From there only 4 lakhs was good particle which we used for this 3D classification, where we are considering that okay, this may be a good class. Here many things are broken after this 3D classification. If you look at this, something is missing here, something is missing, something is missing, or misaligned particles. So we are not considering those are the good class. These are the good class. Only this we are considering good class, which we can achieve a very high resolution structure. So 3D classification is a procedure where you can segregate that 3-dimensional structure, where you can see the high resolution features also. Here you can see this is a spike protein structure, and it has a different conformation. All those structure you have a high resolution features. But if you look at those structures, you can see that all have a high resolution features here, here, here and here. So probably in between 5 to 7 angstrom. But if you look at here, you can see the difference in this particular position. If your protein is flexible, even you can get a high resolution, and you can see that conformational variability using this cryo-electron microscopy technique. So that is the reason it is so important. Here you can see this is called the RBD domain. Here RBD is up and RBD is down, and here RBD is intermediate stage, and here you can see this is the N terminal and this is the RBD, and there is a lot of gap between these two. So you can get different kind of conformation using this 3D classification. Also you have some low resolution structure where the RBD up and N-terminal domain has different position. So using these techniques you can see the conformational variability and different conformation of these protein molecules. So that is the beauty of this study. So here from that you can get that high resolution structure, and all this high resolution structure you can pay attention here, where you can see that conformational variability of this N-terminal domain and this RBD domain. Now next go and discuss about that resolution calculation, that is the most important part in cryo-EM. So there are various methods are available, that Fourier ring correlation, and mostly they are using similar kind of approaches, or Fourier cell correlation, differential phase residual calculation, or spectral signal to noise ratio, but mostly people are using this particular method, that Fourier cell correlation. We will talk little bit about that Fourier cell correlation, how we will do that Fourier cell correlation calculation. So if you just consider you have a 10 lakhs particle for a 3D reconstruction, okay, so we will split this data set into two half, first half and the second half, and we have 50,000 particles, and this splitting will be done in random way, it will be not in same way. So here you can see this is the first set of image and this is the second set of image, and the first set of image will calculate a 3D structure, and the second set of image will calculate a 3D structure, and then we will calculate the Fourier cell correlation, because if you just consider the 3D volume, you know, if you plot this in 3D, so pixel by pixel you will get some at the near the x and y axis, you will get the low frequency signal, and then those will be the high frequency signal that we already discussed multiple times, right. Those will be the high frequency signal and this will be the low frequency signal. Now you have two structure, one is coming from this data set and another one is coming from this data set, and the low frequency signal will be segregated here pixel by pixel, and high frequency signal will be segregated here. Now from this 3D structure, completely independent initial model, when we will refine this particular data set or this particular data set, we will refine it completely independently, and two initial model will use. So that data set, this data set and this data set, they should not see each other. So they should not see each other, they will refine independently. Then we will get a 3D structure of this and another 3D structure of this one, structure 1 and structure 2. Now if we have, this is the two 3D structure we are getting, this is from the first data set and this is from the second data set. Now this is the low frequency signal, so they are very dense white, and now pixel by pixel we are comparing, okay. If we compare those, that okay, this pixel with this pixel, what is the intensity, what is the intensity here, okay. At the low frequency what will happen, that correlation, it will be very high at low frequency, because it will be very strong intensity will be there, and the pixel by pixel, when you measure that low frequency, overall cross correlation will be very high. So this is called Fourier cell correlation. So at beginning, at low frequency, this is the low frequency, if you recall, this is the low frequency, and the cross correlation will be very high. So at beginning cross correlation value will be always very high, until now those are high frequency signal, and when your model has a high frequency details, all the high resolution, then you will get some kind of cross correlation value between those. So now if you try to cross correlate here, your cross correlation part it will be reduced between these two model, and you will get a curve like that, it will gradually reduce based on the frequency, and there is a one value, it is called 0.143. At 0.143 FSC means Fourier cell correlation, this correlation value, what frequency we are getting here, that is called that FSC calculation or Fourier cell ring correlation. So here Fourier cell correlation, if we just consider that, okay, if we just go to this one, that Fourier cell correlation, what we are getting? We are getting that this is the structure factor of structure 1, structure factor of the structure 1, then complex conjugate of the structure factor of the other one, and then it is root square of summation of f1 square and f2 square. this is how we are calculating the FSC. So, here we are not going to discuss too much about this mathematical details, how this cross correlation value look like whenever we will calculate a FSC curve. FSC curve, it will go down, and previously we are using 0.5, now mostly we are using 0.143 resolution, and this is our resolution value or the frequency it is giving here, spatial frequency. And now sometime there is some unhealthy curves are also there, FSC curve. So, this is a unhealthy FSC curve, that FSC curve is always should go down like that, because if you are calculating the comparing the cross correlation between this. So, after a certain time this cross correlation value at high frequency, it will be almost near the 0. So, it reach towards the 0, it should not go up like that, or if it is reaching 0 and it cannot go up again like that. So, those are bad thing. So, why these things is happening? Sometime there is a different reason for this kind of unhealthy curve, but you just remember that FSC curve will be always, it will go down like that. So, here FSC curve does not fall all the way to 0, it rise at a high spatial frequency. This curves was produced by using a very tight mask around the model during iterative refinement. This mask cut through some of the density of the model, producing a sharp edge such as the mask itself is correlating. So, always remember, this is your FSC, this is your spatial frequency, and this is your FSC, and FSC curve should look like that, and 0.143 you should calculate the FSC. So, today's class I covered how to align the raw particle data with your 2D projection and the reference, and then get the 3D model. I also discuss about the FSC, how to calculate the FSC. When you have the high resolution structure, you have to do the docking, you have to do the model building, that is entirely a different course. So, we are not going to discuss about all these things in details. In this course mainly I focus the microscopy part as well as the sample preparation and little bit about the data processing. In future I will design another course where we will discuss in details about the image processing, and I will keep some practical component also where we can show the entire image processing pipeline as well as the fitting, docking and model building and how we can get a atomic model structure from our EM density maps. Thank you all for your attention, and feel free to ask question or email me. So, if you have any question, I will try to answer those things by email, or if required we can virtually meet and try to answer your question. Thank you all again for your attention.